Welcome back, and I've got a really unusual experiment for you today. What I'm going to call this one is weighing an astronaut. So this is a really fascinating bit of physics. Think of the problem about how you would weigh an astronaut. Now you might say, well, it's pretty easy. You put them on the bathroom scales, which is the same as hanging them from a spring balance and seeing how much the spring stretches by and having it calibrated in units of weight, newtons, or in kilograms if you want mass. But think what happens when you travel to different places. On the moon, the gravitational field strength is weaker, and it's different on Mars again. So if we went to Mars, we'd have to change the calibration on all our scales. Well, that's not a problem. But you will have seen a film, I'm sure, of astronauts appearing to float around in their modules. They're not floating, they're actually in free fall. But if they were to hang off a spring balance or stand on bathroom scales, they wouldn't push it down at all. So how can we weigh them? Now, just to get one thing straight, of course, when I say weigh an astronaut, I mean what is their mass? What is their mass in kilograms? That stays the same throughout the places that astronauts travel. The mass is a measure of the amount of material in them. The trouble is we call that weighing them. So think about it. When they're in their space station, they appear to be floating around. They're not floating, but they're weightless. Now, that doesn't mean to say they haven't got any mass. They're still there. They're still solid. And of course, you want to work out, do astronauts get lighter or heavier? Are they eating enough food? Are they staying healthy, etc.? So you stick them on the scales, and every time you put them on the scales, it reads 0. We need a much better way of measuring their mass, one that doesn't use the gravitational field to create a force on them and back calculate from their weight. I remember this really well from school. And I remember my teachers telling me about Skylab, where they had astronauts orbiting the Earth, so apparently weightless, they were actually in free fall. And they wanted to know, are they getting heavier, are they getting lighter, is the food right? And they came up with a very, very ingenious way of working out what their mass was. And what they used was a balance that looks something like this. So I'm going to show you today the tethered trolley. So what we've got here is a trolley on wheels. Now, we don't need the wheels when we're up in Skylab because the thing will sort of stay where it is, if you see what I mean. But it does need to be mounted to the wall of the spacecraft. And it's attached to two opposite walls or to the solid part of the object with springs. So what we can do is we can pull this back and let go, and it'll oscillate from side to side. And the key to measuring how much mass we've got here is looking at the time period or the frequency of the oscillation. So here's our tethered trolley. Yep, we've got the trolley, which would be the seat for the astronaut. We've got springs on either side, and it's an oscillating system. Now, think very carefully. The gravitational pull on this is downwards, and that's at 90 degrees to the movement of this. And most of you will know that if a force is at 90 degrees to the movement of an object, it doesn't affect its motion. In other words, if the gravitational field in my laboratory got a bit stronger or a bit weaker, this would still go from side to side exactly the same way as it is now. There might be a little bit more friction, but it'll still have the same frequency. It'll still have the same time period. So what we need now is an astronaut that we're going to weigh. So, to demonstrate how this works, we need an astronaut. Well, we've got Laika. I suppose Laika's a cosmonaut because she was from the USSR, so I suppose cosmonaut, not astronaut. But if we put her on the seat and pull it backwards, it's very difficult to see, but the time period of the oscillation, the tick, 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 is slightly lower because the whole thing is slightly heavier. And if we take her off, the time period should be just a little bit shorter because the total mass is smaller. But I can make that more obvious by putting a larger mass on here. The point I'm making is that the frequency that this oscillates at is mathematically connected to the mass that's on here. And what I'm trying to show you is, as the mass goes up, the frequency of the oscillation, how often it goes up and down in a second, goes down. In other words, the time period goes up. And that connection will allow us to work out how much mass is here without worrying about the effect of the gravitational field. So let me show you more clearly that there's a connection between the mass of this system and the time period of the oscillation, the time taken to do one oscillation. So we won't get a stopwatch out and do any complicated calculations, but if you look at this one, it goes tick, 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 tick. It's quite light. Let's put our astronaut, our cosmonaut on it. So we've increased the mass of the oscillating system. And look what happens now. Tick, tick, tick. It dies away, but the frequency is much lower. The time period is much longer. So there is definitely a connection between the mass of the system and the time period of the oscillation. And we can use that to work out the mass of the astronaut. And all we need in our spaceship is a chart of time period against mass that was calibrated on Earth, and we can work out the mass of the astronaut. But there is something interesting that we can do to show I'm not cheating. We can get it to oscillate with the heavy or the large mass, and then I'll just lift it off and see if you see the frequency of the oscillation increase. So here we go. Big mass, small mass. So the frequency goes up and the time period goes down. So we now know there is a connection between the time period of the oscillation and the mass that's on it. And it's totally unaffected by the gravitational field. So if you followed that, all you need to weigh an astronaut in space where you're not using the gravitational field is you need a table of data that says what's the mass here compared to the time period of the oscillation. And as you change the mass, you can look up on your table of data what mass would give the time period that you're measuring in your spacecraft. So a really clever way to measure masses, how much material is in an astronaut, in space where you can't use the gravitational field. And we call this in physics labs the tethered trolley. So I do hope you enjoyed that experiment and you understand a little bit more about how we would weigh or find the mass of astronauts, especially when we travel out to Mars. It's a complicated experiment, but the main thing to note is this connection between the frequency of the oscillation or the time period and the mass of the system. Anyway, I hope you enjoyed that video and I look forward to making another one for you very soon.